So let's talk about how to make these networks a little bit less complex. And so how can we actually make these really computationally expensive neural networks a bit smaller without losing too much accuracy? Well, networks in networks has been proposed as a convenient strategy for doing this, and initially the community didn't perceive this very well. Actually, people were slightly amused about this idea because at the time it didn't really outperform existing solutions. So an idea is, if you look at this figure here, and this comes from the original publication of Network in Networks, you see that there's a multi-layer perceptron inserted as an intermediate layer in this convolutional network. So actually several of these MLPs are inserted in here, and this sounds a bit crazy at first, because why should you do this? Why shouldn't you have the fully connected layers just at the end, like in AlexNet and LearnNet? When that idea was published, people thought that this was a little bit silly, because it didn't really outperform what was out there at the time, and it needed one more iteration to get then basically the state of the art what we use now. So if we look at the last layer of this LearnNet here, just a vanilla LearnNet from the original paper, well, that output here, the whole thing is not so big. So I mean, it's basically, the output here is basically just 120 hidden units, and 84 and then 10 for the output here on this MNest example. In AlexNet and VGG, well, those things get quite massive, especially if you look towards more output classes. So if you look at the last layer, just connecting from the convolutions, you have a number of channels times the width and the height of the last resolution here. That was 48,000 parameters in LearnNet. In AlexNet it was already something around 26 million parameters, and in VGG 4 times that number. So that grows quite rapidly. Whereas convolutions were actually quite well behaved in this progression. It's usually input times output times convolutional kernel size. So that's not too bad. If you had a kernel size of 3, for example, then that's 9 times input times output. So that's actually quite well behaved. But those last layers are the ones that really made life hard back then. So the question is, of course, how can you fix it? And the issue is, well, the issue is, in the end, you need to produce something that's of a dimensionality that matches the number of classes you want to discriminate here. At some point, you need to go from a 2-dimensional times channels representation to something that's a vector. The challenge really is how do you do that? Now let's have a look at that in a bit more detail. If I print the size distribution for VGG here on that slide, you can see that as I'm going from sequential 5x5s, so this is basically the last convolutional block. So that's 5 times 12,000 or so channels with 7 by 7 to a 4096 dimensional output. That really needs a lot of parameters and a lot of memory. So it's computationally very, very expensive. One way to address this is to get rid of those fully connected last layers. Well, you don't say, right? How do you get rid of such layers in the end? You need to somehow convert your 2-dimensional feature maps to some 1 by number of classes vector. Sounds quite easy in theory, but how do you do this now? So the problem is convolutions and pooling reduce the resolution, so you keep on having things, but then at some point you still need to map to this number of classes at this output. So you also need, well, in between you need some degree of nonlinearity to mix and transfer the information between the various channels into as expressive and representative representation that works for your number of classes, and also generalizes to other cases. So this is exactly where one-by-one convolutions come in quite handy. If you remember back a few videos ago, we talked about one-by-one convolutions and what they actually are. Now we can really make use of them. So if you remember, they only act per pixel on all channels. So this is actually a multi-layer perceptron applied to each pixel, so to pixel-wise activations. So in the end, you only have maybe a 5x5 activation wide resolution, then this really allows you to get a large amount of per channel information quite nicely presented in the form you would actually need. So in the very last layer, essentially they just got rid of the fully connected layer. So rather than bothering with one last dense layer, they just performed global average pooling at the end. So if you look at this again, well, the one-by-one convolutions is just a multi-layer perceptron. So that's what can address the issue. If we move back all these fully connected layers into the convolutions, then we can actually achieve the same effect by not having fully connected layers at the output, but instead using something like global average pooling. This led to something called an block network block. So it's a network block then. So you basically have convolutions followed by two one-by-one convolutions, and these act like an MLP. So this is basically the same as if you would have a dense layer in that, and then you repeat this a few times and you get the following architecture, which is which is this network block. So the new network had a number of convolutions followed by that one-by-one convolution, max pooling and so on to reduce the resolution, and you did that 3 times in order to get meaningful network representation. And this completely got rid of the dense layers, which was the contribution of the network in networks. They didn't perform quite as well as VGG, which is one of the reasons why people initially overlooked it, but later that really took off in Inception, for example. But well, they were a key concept. These kind of convolutions, these one-by-one convolutions within the network, were a key concept in order to get things like Inception and ResNet, which we will discuss next, really going, and we'll talk about this in a bit. So the network in network architecture is shown here on the very right, and if you compare it to something like VGG, where you have this massive final fully connected layers, there is now just global average pooling at the end, and all the fully connected convolutions are replaced by these one-by-one multi-layer perceptron style convolutions within the network as blocks. So now we have these NIN blocks here, which just make up a network in network architecture. Okay. So this is a little bit repetitive. In PyTorch, it's getting not much more complicated than any other network implementations. So this network was then very quickly superseded by Inception and ResNet. So I'm not going into too much detail here. You can look the actual implementation up in the PyTorch documentation. Let's look in something quite similar, but a very popular network right now, which is Inception or GoogleNet, and I wrote it the way like the kind of intention of that word was is Google and LearnNet combined. So that's how it looked like, and this is from the original paper from the authors. It's, well, what you can see here, it's on the one hand it's deep, and this is the first time that you probably see parallel paths in a network. So far we had only one path to the network. Now we are using several paths at once, and we'll talk in detail now why we would actually do that. Now, I mean, if we compare what we did so far, on the very left we have LearnNet, and so on the very left we have LearnNet here, and so this has 5x5 convolutions, and then AlexNet, who use these 11x11 and 3x3s and 5x5 convolutions. Then we looked into VGG. I'd used some other mix of tools, and then, well, the network and network was mostly 1x1 convolutions. Well, this is quite a mess, right? So what shall you use? 5x5s, 3x3s, 1x1s, max pooling. Well, you don't really know what you should choose for a particular problem, right? So the 1x1s, the 3x3s, and the 5x5s are max pooling or multiple ones. And yeah, I mean, you can't really decide on these here, right? So this was essentially the dilemma they had back in the day, back in the day in the deep learning Stone Age, so a couple of years ago, when they tried to figure out how to build good convolutional blocks. So the issue is the following: if you pick so the issue is the following: if you pick 5x5s, you end up with a fair number of parameters. So your parameter space gets quite big, and you end up with a lot of multiply add operations, and those things can get really costly quickly computationally and make your network slow, and also the training slow. A lot of parameters, so also mean it won't generalize that well, but it's on the other hand very expressive. So on the other side, if you pick 1x1 convolutions, then it's very well controlled, and it doesn't need much memory area, but at the same time, well, it maybe doesn't work so well for your actual program. So what are you going to do? So the solution was actually not to decide, and that was actually a brilliant idea. When this was published, and yeah, it's also called the Inception network. These are the figures from the original publication, and they called it Inception network because they wanted to go deeper, and that was literally their motivation for coming up with their name. They wanted to go deeper and deeper, but couldn't achieve it with traditional blocks. So they chose blocks where you don't have to decide which convolution to use. So here's the Inception block, and it's really, here's the simple version of the Inception block. Here is what is currently more or less used in Inception V1, and it's really, well, they don't know, so we don't know what to choose. It has 1x1 convolutions, it has 3x3 convolutions, it has 1x1 followed by 3x3, it has 1x1 followed by 5x5, it has 3x3 max pooling followed by 1x1 convolutions. We just combine this all and hope, well, if you throw it all at the wall, something will stick. This is just a simpler version, so it doesn't really matter what you do here. There are some variants then and certain versions where they propose better combinations of these blocks, but the basic idea is really you don't choose. You let the network decide during learning which ones of these paths might be the most suitable ones for your problem. Now, to make sure that this all has the same dimensionality, you need to use the appropriate padding, of course. So that's why they use They use 3x3 half padding by 1 by padding by 1 by 5 by 1 5 by 5 and half padded by 2. So at least in terms of sizing, the inputs and the outputs have to be the same. So this comes out as to be the same size. And then you actually just stack it all together, and you put several of these inception blocks together to get your inception network. So you now have an architecture with different channels doing different things, and the hope is one of these channels or paths through the network is gonna work for whatever the dogs and the cats in your images, or for it's going to work for the dogs and the cats in your images, or for the birds, and so on. So this is the inception block. Now you probably might wonder why this block should be actually a good idea. Well, they probably tried out a few things, a few variations in the beginning, and that block worked the best. You could also think of combining 11 by 11s, and there were 7 by 7 convolutions in the same way, but apparently that worked best to beat the benchmarks at the time. So let's for now just assume that this was a trial and error approach, and then this was what really came out best. So for instance, if you look at the first inception block in an inception network, well, it uses 64 channels here for the 1 by 1s and 128 for the 3 by 3s. So 32 for the 5 by 5s, because they have a lot of parameters already anyway, right? So it's, I mean, if you think about that, it's here 25 times 32. So in the other case, it's 9 times 128. So you have just a few other max pooling dimensions thrown in, because, well, you want this all to add up to 256 right here. So you need to make sure that these dimensions really fit your constraint, that input size needs to be equal to output size, right? So there isn't anything terribly deep in here in this one yet. The number of input channels doesn't really matter too much at this point. It's just features in right channels in, and then you get some appropriate number of channels out, right? So that number of channels doesn't really matter at this point, but the tensor dimension matters a lot for this type of blocks. But what it really does is that you now have a number of parameters, a number of floating point operations basically, and that they actually, the fun part of that is really actually that bigger block here is doing something a lot more simple and has more benefits, and is computationally actually cheaper, as if you would just use a homogeneous choice of 3 by 3s or 5 by 5s in these sort of blocks. So if you do a parameter count and say, well, if I want to have 256 output channels, well, 256 output channels, then with Inception you actually only need 160,000 parameters, and this number of parameters, this costs you about 128 megaflops. So it's also a very kind of efficient network in this context. Whereas if you would choose homogeneously across all these convolution blocks, 3 by 3 convolutions, that would cost you about 3 times that, and 5 by 5 is about 8 times that amounts in terms of floating point operations per second here, and this well scales accordingly the bigger you go with the convolutions. So the assumption is still if you know if you can get the same thing done with fewer parameters, then and they work better, then yeah, this is essentially what you should go for. And the Inception network ticks this box basically, and is relatively efficient for what it can achieve. So why is that kind of heterogeneous choice of blocks actually more efficient? Let's quickly look at the algebra. So for a particular layer, we have k by k, so in this case, say square k squared as a kernel size. So since they are like 3 by 3s or 5 by 5s, we can just assume k squared here. And then we have this whole thing times C in, so number of channels input, number of channels output, and then I have basically the tensor height and width of the image in this case, for example, whatever I've put in here. Well, get my pointer. Well, this one is fixed, and this is also fixed. I can play around a little bit with that if I want. And then, you know, what you get in the end is basically a sum of all of these convolutional blocks you have in your inception block, right? So this, if this is homogeneous, then this is of course large. If this is heterogeneous as it is proposed in the inception block, it hits a better spot in terms of computing. Okay. Okay, so here is the network in its full beauty, and this is representation is from the D2L book. It's a little bit easier to understand than what they had in the original paper, and I would really recommend the D2L book here at the bottom of the page to have a look at. It's really well written by Alex Smaller and colleagues, who gives an introduction in this and also provides code examples, not in PyTorch but MXNet, but both are quite similar, so you can easily translate between them. So finally, there are 5 stages, right, in the Inception net, and the stage 1 here really behaves very similar to a lot of the other convolutional networks that we have discussed so far. So it starts with a fairly broad convolution here, and pooling. So we reduce the resolution immediately after broad convolution, and then we go into a little bit more 1 by 1 convolution, 3 by 3 convolution, and then pooling. And then stage 2. So stage 2 here is again much trying to get some overall spatial correlations, and then some pooling operations to break down the dimensionality for the following inception blocks. So this is stage 1 and stage 2 are fairly common across all of these neural networks so far, and now is where all the interesting things start to happen, because we now have those inception blocks from stage 3 on. So 2 of them, in fact, in stage 3, they're just stacked on top of each other. So this 3 by 3 max pooling, each of these operations halves my resolution. So what I'm doing is I'm shrinking the resolution, but I'm also increasing the number of channels, because now, while I have fewer pixels, they have more valuable, more high order information that I'm going to use later on in my network. Then I have a backbone of basically 5 inception blocks, one after the other. This is where most of the interesting nonlinearities happen in this sort of network. They shrink again, and then I'm picking 2 more inception blocks here. So why did they do a split of 2, 5, and 2 inception blocks here? Well, they probably tried out a whole bunch of combinations and networks, and that's the best thing they could come up with for this particular benchmark they were looking at, not like an ImageNet. There are some follow-up papers like AmoebaNet, which are quite interesting and beyond GoogleNet version 4, where they essentially use a genetic algorithm to just randomly try out whatever stuff works best for these kind of inception blocks and what sort of combinations works best for a particular problem. So, well, if you have the compute available and the time and cost is not an objective, then you can do approaches like this. The average machine learning researcher might probably not have these sort of resources, so you'll have to use probably networks as they come out of the box, like this Inception here. So let's look at stage 1 in a bit more detail, and so if we compare the two, so in AlexNet basically, in AlexNet it's basically a very wide convolution in the beginning, an 11 by 11, and monitor followed then a little bit smaller. It's only in GoogleNet it's only a 7 by 7, right? So you have then followed. This is then followed by 4 1 by 1s, and then again 3 by 3 and pooling. So it's not too dissimilar from actually AlexNet. That's just stage 1 and 2. The only difference is that you have a bit more channels in here. So in AlexNet ended up with 12 by 12 in the end. This is and this here, this InceptionNet is 28 by 28, so it's still keeping a fair amount of the information that you wouldn't have otherwise. So stage 3, well, a fair amount of stuff is already happening, and so the allocation is different between channels, even between the first and the second block here. So you can see for the first block you have 256 channels here, and the second you have then 480 coming out of those. Then you actually go and reduce the resolution, so you can start out with a 28 by 28. In the end you get a 14 by 14 resolution from these first two blocks. The different versions of those networks are usually due to different size trade-offs, and whether you use 2, 3, 4, 5 stages or blocks in the beginning, and then dependent on the composition of these blocks. So Inception has various versions, and all of them are basically due to block composition and network composition differences. Now stage 4 and 5 look very similar. Again, you increase the number of channels to 512 and then 832. Well, why is that? Why do you do that actually before the max pooling? Well, because the max pooling shrinks the resolution, so we better store as much information as we possibly can do on, in this case, a per channel basis. And then in the end you have basically 1024 output channels, and that just so happens to be the same size as what you would get for the number of classes that you want to predict, at least for example in ImageNet or something like that. And then you just perform a global average pooling, and now you pool together all these channels to get one final prediction. And now, and this is actually a great idea to just do this global average pooling then later on a 7 by 7. So this works reasonably well then for making predictions and classifications. So there are various flavors of the Inception network. There is, for example, Inception PN or Inception V3 and V4. All of them are modifications of the network architecture. The thing is, of course, they all improve benchmark performance to some degree. Architecture patterns are changed, so we add something called, in Inception PN for example, something called batch normalization, which we'll cover in a bit. and V3 adds different shapes of convolutions. So this is going even crazier on, well, the need for the 3x3s, and then you do not square kernels, for example, you do 7x1s and so on, and 1x1s, and over making each of these blocks even deeper. And this is exactly where if you didn't try out even more things, you might end up with something like AmoebaNet, yeah, which does that automatically for you. So, and the Inception V4 then later copies parts from the RaiseNet architecture, which we'll also cover in a little bit, and incorporates residuals into the Inception network to make it on par with any state-of-the-art architectures that are currently out there. So let's have a look what changed in Inception V3. On the left-hand side is version 3 for stage 3. And if you compare left and right, you can see, well, in the right hand side replaced its 5x5 convolutions with 2 3x3s. Okay. So if we compare this, so we have here now 2 3x3s, and this is actually what you would expect. So if you remember when I mentioned the Simonian Sisserman paper, there was actually the question if bigger and wider convolutions are better, or shallow and deep, and deep and narrow. So deep and narrow obviously won back then, and this is also the finding here in version 3. So you do more narrow and deeper convolutions, which give you a better performance eventually on this benchmark task. So that's why they replaced this, and this is, well, this is a fairly benign change, right? Now let's look at stage 4, and this is where the big changes actually happened in version 3. Again, we have these 5x5s in the old version, which we want to replace by something, but now this is now replaced with something, well, at the first glance slightly strange, with 1x7 and 7x1 convolutions. This is actually the first time that people used asymmetric convolutional shapes for real. So 7x1 is quite narrow, right? But it requires only 7 parameters. A 3x3 requires 9 parameters, right? So it is a little bit cheaper, and it's a bit in the direction to approximate separable convolutions. So this increased the computational budget, and again outperformed through that previous versions. So those 4 layers of 7x1s and 1x7 convolutions that are alternated cost you only 28 parameters, which is quite cheap. This means the cost is actually quite similar, but your expressiveness and receptive field is larger through such an approach. So you see more of your environment. So why would you combine then 1x7s and 7x1 convolutions? Why can't you just get away by using, saying just 1x7 convolution? Well, why do you need both? Well, if you only use the 1x7 convolution, so this is just one kind of square like this, and the other one is a square like this, is a rectangle like this, so 7 components vector. Well, if you only use one of them, then you would, for example, just see the vertically continuous features in some way encoded in your network, and the other one just the horizontal ones. So horizontal features 1x7, 7x1s, horizontal 1x7 vertical features, and you probably want to have both. Well, it depends a bit on your application. If you know that your task will be predominantly defined by one or the other direction, then you might be able to get away with it by just using 1x7s, for example. If you want to solve a general task, then you should actually combine these so that you can have a fair amount of vertical, horizontal-ish aligned features in some way. So So this is Inception V3. You can directly use it through PyTorch Vision, for example, and activate this model and put it on your classification task. So this is 7 by 1s and 1 by 7s. So now in the stage 5 even went a bit crazier. Then if we compare stage 5 from the old version and now the stage 5 in version 3, again these are from the D2I book. Then these illustrations are from the D2I book. Then you see that, I mean, this stage is pretty crazy. So rather than those 3 by 3s, it used 1 by 3 and 3 by 1s, and likewise in the other part. So okay, so I guess you can see the pattern of what the modification steps were. So replacing dense square convolutional kernels with more sparse and kind of linear convolution kernels. That was really the main idea in the later versions of Inception. And with that now, we are at the point where we are getting closer to what's actually state of the art right now. And really, if you have a vanilla classification task, you would probably pull out one of these networks, Inception V3, to do your cats and dogs classifier, and just let it loose on your data. And what you will see is that a lot depends on the actual data you train it on, and that the impact of the actual network architecture since Inception 3 and then later ResNet is not that important anymore, right? We have very expressive, very powerful representation networks right now. So what people started to look into later is how to change the training data, and we'll also talk about this in a bit. So this is this plot here is from Gluon. This is a plot of accuracy versus throughput for a quite large number of models. So what they did is they re-implemented all of these models, put it on the same, exactly the same task with the same, in the same training environment, same learning rates, everything, and evaluated the actual performance on that particular task and put it in the plot. So they were trained in the same way, and each dot corresponds to the amount, so the dot size corresponds to the amount of memory footprint that is needed in order to execute that particular model. So you can see the VGGs here are pretty large here, while Inception is kind of, well, average, more or less here now. So small dots are very efficient models, and higher up ones are more accurate. So this is a very efficient model but not so accurate. This is not so efficient model but highly accurate. And it is these are the ResNets. So we are here in this area. This is Inception. Not this in particular is Inception V3. So the lines here also show something interesting. The lines actually show the reproduction by people from Gluon, so they reproduced it and compares it to the published results. And some of these models show quite a significant gap, which means the training environment was vastly different between the published results and their training environment here. But it gives an approximate idea where it should be located. So also an interesting observation on these charts is you can actually navigate around on these charts with an engineering approach, and say if you want to land in a particular spot, well, depends on what you do. You have probably two choices. If you only want to beat a benchmark or put your model somewhere in a particular location here on this chart, then the easiest way to do this would actually take any of these models here and to put, so let's say this model and this model, and I want to land here. So the easiest way for a benchmark setting would be if you, for example, give half of the data to this model and half of the data to this model, then you will land exactly in the middle here. The other alternative, if you have not a benchmark setting, but if you want to do something in a more test-related setting, is you can ensemble several of those, so you can actually distribute your data to several of these models to land somewhere in the middle of them. So if I distribute my data equally to these three spots here, I will likely somewhere at the end land here. Of course, that would also mean you have to add up the memory footprint of those, and your model would probably move altogether a little bit more towards a larger model here on this side. So you'll probably be skewed towards this direction. But if accuracy is your only concern, you'll probably be well off with an approach like this. So what do we learn from that? Well, first, dense layers are computationally and memory intensive. So really dense layers is what you try to avoid in big models. Real world problems with big input tensors and many classes will probably prohibit any use of deep networks if you use something like AlexNet or anything that has a very expensive fully connected tail. Again, one-by-one convolutions, they are pretty important. They act like multi-layer perceptrons per pixel. Maybe also an interesting observation in this context is that scientists are also just humans and sometimes need a while to understand the power of new approaches and integrate it later. In this case, it was networking networks, which was extended to Inception and then suddenly dominated the field, while initially it was not taken seriously. So if in the case of Inception, what they really showed that if you're not sure what kind of architecture to use, just take all of them. Take all options and let the optimization decide for you, or even learn this through trial and error. So the overall composition can be learned through genetic algorithms, some brute force trial and error, to end up with something like AutoML, where you get a bespoke network architecture for a particular task at the best possible outcome for the required compute resources.